Hi, my name is Meredyd, and this is Midnight Story Hour because it is 1 minute to 4 in the morning here in the UK. Today's talk is brought to you by the letter Z and a very, very large pot of tea. So I am here today because the web is for wonderful as it is, it's a mess. It's a terrible environment to program in. And those failures are failures of abstraction. So if we want to understand what's wrong with the web and how to do better, we need to understand abstraction. Abstractions. What are they? How do they leak? How do they fail? And what to do about it. So, what's an abstraction? Well, I mean, it's a very overused term, but it's a way of representing some complex low-level system in a way that's easier to work with. And this is a pattern we see throughout all computer systems. To make it a little bit more concrete, let's try some examples. So, a hard disk is, as far as the rest of the computer is concerned, a fixed length slab of bytes that you can read and write. So you can ask the hard disk, what's the byte at the position, 1,000,012? Please write the value 42 to the byte, 2,000,057. And that's not actually a very useful interface to program against. So the operating system gives us this abstraction of files, which are bags of bytes you can arbitrarily grow and shrink. You can edit things in the middle of. They are organized in this tree of directories, and that is a much nicer interface to write programs against than just a big slab of bytes. And of course, underneath it is the operating system's implementation, which is translating from the abstraction of files and bags of bytes onto working out where each little bit of data that you're reading or writing is actually located in this great big sort of flat slab of bytes that is the disk. And of course, I should say that the disk, being a flat slab of fixed size array of bytes, is itself an abstraction, and inside your hard drive is a microcontroller working very, very hard to present that nice tidy abstraction on top of banks of flash chips or spinning iron oxide. It's turtles all the way down. Here's another example. The internet. So the internet is itself a really powerful, awesome thing. And the thing that makes it so powerful is that I can toss a packet onto my local wireless network with an address on the front saying, please deliver this to a computer in San Francisco, without any idea of how to get there. And the vast majority of the time, the internet will route that packet through heaven knows where, and it will re-emerge in San Francisco, which is a really cool property, but it's not 100% reliable. Sometimes it won't get there. Sometimes it'll arrive twice. Sometimes they will arrive in the different order to when I sent them. And to make it easier to program against, we invent this abstraction called TCP, Transmission Control Protocol, where we say, well, I'm going to set up a connection to a computer at the other end, and the abstraction is going to be that I'm going to send a series of bytes down this connection, and these are guaranteed to arrive. They are guaranteed to arrive exactly once, and they are guaranteed to arrive in the order I sent them. And this is an abstraction that is much easier to use as a programmer and is therefore used for most of the internet technologies that we use today. Here's one a little bit closer to home. A computer processor is a very smart lump of silicon, but fundamentally it can only do a very, very simple, small and simple set of operations, like primitive arithmetic operations, reading and writing bits of memory, and that's a terrible interface to program against. So what a high-level programming language like Python is an abstraction over that. instead of having to interact with these low-level CPU instructions, we can instead interact with this abstraction where we can just define a function, call a function, add, make complex expressions that nest function calls and arithmetic operations and all sorts different types of data that aren't just numbers, and that's a much more pleasant abstraction to program against. And the Python interpreter takes care of giving us that abstraction on top of executing low-level CPU instructions. So, I mean, this really is a fundamental concept to computer science. It was actually invented very quickly as this famous quote that every problem in computer science can be solved by another layer of abstraction, from David Wheeler, a very early computer scientist, one of the original greats here in Cambridge. And it really is true, because this is how we solve most of the problems of computer science. Indeed, a computer is so bafflingly complex that these sorts of simplified abstractions are the only way that any person's human mind can actually usefully make use of these things. There is, I can say confidently, nobody on Earth who actually understands at the most gritty level absolutely everything a computer does. It's just too much to fit inside a person's head. Abstraction is the only way we can cope. So they are great and they are essential, but they're not perfect. Famously, abstractions tend to leak, by which we mean the way your abstraction behaves depends on the actual underlying implementation. So, for example, if you're dealing with files, it's usually faster to read a file straight from the beginning to the end, rather than hop around within it. And this is the reason for this is where exactly the sequence of the contents of this file are located across the bag of bytes that is the hard drive. So the details of the underlying implementation are leaking up to the user of the abstraction. In the same way, the way that TCP creates this reliable channel on top of the unreliable network of the internet is to send acknowledgements back and forth and time out if it hasn't received something that it hasn't received acknowledgement for something that it sends, and try again. And if you are using TCP or using something built on top of TCP, what this generally feels like is a single packet loss can suddenly bring your SSH session or web browsing to a halt, and then there's this weird kind of timeout while it tries, and then it suddenly all starts working again. And what that is the implementation details of an abstraction you're using leaking up to the point where they're visible to someone using a high-level abstraction who was supposed not to have to care about the details of packets on the internet. But it gets worse than this, because abstractions don't only leak, they fail. An abstraction fails when it prevents you from doing something that the underlying system is perfectly capable of. So let's take TCP again. The internet is very, very capable of doing fire and forget single packets. That is in fact all it does. But TCP enforces this ordering, this waiting, this retrying, which means that if you want to, for example, do real-time media, broadcast video over the internet, who would want to do that? Especially live. You actually can't do it on top of TCP, because if one packet gets dropped, the rest of the stream gets held up, waiting for the timeouts and the retransmissions and the acknowledgements, so that they all arrive exactly once and in the correct order, which is murder, right? From a video point of view, we'd much, much, much rather drop a frame of video than have everything come to a grinding halt, for several seconds waiting to retransmit. But tough, because if you did that on top of TCP, you just cannot make that trade-off. In Python, the implementation of the Python interpreter is very flexible, very abstract, and so the way that Python handles math is slow. It's just not possible, really, to do high-performance numerical computation with Python. The individual arithmetic operations and logic operations are just too slow. You can't do it, even though the underlying system, the CPU, is very, very capable of doing high-performance numeric computation. The abstraction has failed. So while we're talking about abstractions that are not doing nice things to us, let's talk about the web. And the web is an absolute mess of abstractions piled on top of each other. If you're familiar with web programming, think about it from the perspective of your data. Your data will probably, in a typical web application, will probably start out as a row in a database table, accessed via SQL. But your code will immediately turn around and transform that into an object in some server-side programming language, probably a Python object, with methods and attributes for accessing it, which is a different abstraction of your data, which you will then immediately turn around and expose as JSON over HTTP endpoints, which is a very different way of representing your data. And on the other end of those HTTP requests is some JavaScript that's reassembling that data back into client-side objects and then transforming it into HTML DOM, which is a different sort of object, and then transforming that with CSS to pixels on the screen. And that is a lot of different representations. And most of the day-to-day work of web programming is translating between these different representations of your data. And that is tedious and repetitive. And that sort of tedious and repetitive thing invites the wrong sort of magic. What do I mean by the wrong sort of magic? Well, let me illustrate by taking a totally unfair potshot at SQL Alchemy, which is a library for automating the conversion between rows in an SQL database and Python objects. And this is an unfair potshot because it's actually really cool. It lets you write expressions like this: query, book, filter, book.price is less than 20. That's nice. Of course, the process that takes this Python expression and turns this into SQL you can execute against the database is black magic. We are talking meta classes. We are talking Python operators overwritten to do something completely different to what they normally do. If you think that book.price is less than 20 is the straightforward numerical comparison that it looks like, you're in for a nasty shock the moment you try to edit that expression. Another way of putting that is, this is an abstraction that leaks like hell. In order to properly use a library like this, you need to understand how the Python is working and how the SQL is working and how SQL Alchemy implements that abstraction. And so all the details are leaking up to the user. And maybe that's worth it if, in order to save you some typing time, if you do it once. But if you have this much abstraction that's this leaky at every layer of this stack, you're going to have a bad day. But of course, that's exactly what we do. We have ORMs like SQL Alchemy turning database rows into objects. We have REST frameworks helping us expose those objects over HTTP. We have JavaScript frameworks on the other end helping us reassemble those into JavaScript objects. We have templating engines helping us turn it into DOM, and we have CSS frameworks helping us turn it into pixels. And all of these are incredibly leaky abstractions that force you to know about way too much to use them. They say that every problem in computer science can be solved by another layer of abstraction. Well, except the problem of too many layers of abstraction. We're Pythonistas here. How does that stack up against PEP 20, the Zen of Python? Simple is better than complex? That is not a simple system. I think we can all agree here. What I've just described is not a simple system. If the implementation is hard to explain, it's a bad idea. Not only is the implementation of something like SQL Alchemy or React really quite complicated, But you also need to know all about how it works in order to use it at any advanced level. So it's not just hard to explain, it is necessary to know. It's the worst of both worlds. This is a famous one. There should be one, and preferably only one, obvious way to do it. Oh boy. So I'm not just ragging on the web. I mean, I am ragging on the web, and I think I'm justified in doing so, but PEP 20 isn't just like a set of weird, kooky community norms from this community of Python. PEP 20 is a guide to building good abstractions, which shouldn't surprise you if you think about Python, the language, as an abstraction over programming. These are rules to help us build abstractions that are useful. So how could we do better? And this is very much what we set out to do with Anvil. Okay, so this is a pain. How could we build something that was more in tune with those values that was for the web? How could we build a better abstraction? Well, the first thing to say is, well, pick one for heaven's sake. Don't have 5 of them knocking around here. And the abstraction we chose is the Python programming language. So we replace all of these frameworks and all of the transformation between different representations with Python. And what this means in practice is a Python GUI framework for the browser, so there are components on your page that are just Python objects. Running client-side Python in the web browser, which means that you can drive your UI just by manipulating Python objects, rather than, say, generating code in a different programming language, because that would be crazy. Who would do that, right? Python on the server, obviously. But of course, once you have Python on the client and Python on the server, you don't have to mash everything through JSON and HTTP anymore. You can just make a function call. We even have a database that naturally thinks of rows in it as Python objects, which means that your data is actually in the same abstraction all the way from the back to the front of your application. And that buys you an awful lot. Having talked about this as a general set of principles, I'm going to show you what I mean by showing you what it looks like to use. So, right, you should be able to see my screen. Okay, so here I am inside the Anvil editor, and I am putting together a new web application. So, try and zoom that one in. Okay, this is the Anvil editor. This is a web page, and this is a toolbox of things I can put onto that web page. So I'm just going to build like a quick hello world type application to illustrate the principles that we're talking about here. So I'm putting a piece of text on here to prompt the user to enter their name. I'm going to put a text box here so they can answer that question. I'm going to call it name box. Everything in Anvil has a variable name, so we can access it from code. And then I'm going to put a button here for them to click when they're done with that. And you can see what's going to happen, right? They're going to enter their name and click a button, and a greeting is then going to appear. So here is the label where that greeting message is going to appear. I'm going to call it message label. And we can change some other properties of this thing as well. We can make it center aligned, and we can make the font big and so on. So I just built a web page, and sure, that's faster than how I could have done it with HTML and CSS, quite a lot faster. But the really cool thing is it's all backed by Python. So if I double click this button, I'm now editing the Python code that runs when this button gets clicked. And you can see that all the things I've dragged and dropped onto my page are available as objects in my Python code. So if I want to set the text on that message label to be hello, and then the text from the name box, I just write it as a Python expression. All right, so we have a working application. It's actually already live on the internet. So hello Python SF. Oh, SF Python, I'm sorry. I did not erase after I did my rehearsal. Excellent. Okay, you could go to hello.sfpython2.anvil.app right now, and this app is live. So we've just built and deployed a web application with nothing but Python in well under 2 minutes.
Meredyd, would you mind just posting that link in the chat so that we can all
sure. Okay. Well, let me go and delete the app I created in when I was rehearsing, because that's just embarrassing. And then I will give it I'll give it a slightly nicer URL. There we go. Okay. Hello sfpython.anvil.app. Right. Into the chat here. Sure. There we go. Okay, so that app is live. Now, of course, we've just done this all in client code. So this is the Python. This Python gets compiled to JavaScript and runs in your web browser when you visit, which is kind of neat. But obviously, any serious-sized application is going to need some server-side code as well. So what we can do here is we can add a server module, which is a Python module that runs on the server, ordinary Python module with an ordinary Python function. What we can do is we can tag this function anvil.server.callable and say this function on the server is something we ought to be able to call from the browser. So if we now go back to the browser, and when the button gets clicked, as well as updating the UI, we go anvil.server.call, and we call that say hello function, and it wants a name parameter. We pass in the text from the text box. And now when I run this, you can see when I click the button, I've got some output in the log file. That's the print statement running on the server. And now we're properly in business, because obviously there's limits to what you can put here, what you can compile to JavaScript. But over here, this is a proper Python interpreter. You know, if I want to connect to a database, import scikit-learn to connect, go. You know, I want to run SciPy, NumPy, TensorFlow, whatever, just import it and use it. It's just Python. In practice, the first thing everybody asks is, so how do I connect to a database? So we actually have a built-in database in Anvil here. It's backed by Postgres, so you can stuff gigabytes and gigabytes into this thing. I'm going to be a little bit less ambitious. Here, I'm just going to store all the names that get entered. So I'm going to have a column for the name and then a date time for when it was entered. And that's it. I've just created my user interface. Excellent. The demo gods are with me. Something is syncing in the background. So this is apptables.visitors, and it's accessible from my code in exactly the same way as those text boxes and buttons were. So as well as printing this message into the logs, I can take apptables.visitors, I can add a row, I can fill out the name with the name that's been passed in. I'll fill out when with datetime.now. And now if I run this, go into the data tables, and you can see that we've actually added that data to the database. So we've just built and published a database-backed web application with nothing but Python, and we're still not even cracking 5 minutes in. I'm going to show you one more thing, because it's going to be relevant later, which is how we take this data and we display it back on the screen. So we want to display all the names that have been entered so far when you open the app. So the first thing is to write a server function for retrieving all the visitors. And we're just going to return apptables.visitors.search, which returns a search iterator. I'm not going to specify any conditions. I'm just going to return everything. And now we go to the user interface, and we add some UI for displaying it. So I'm going to add a data grid. I'm going to give it 2 columns, one for the name. It's going to pull out the name key of everything that's given, and one for when entered, which is going to pull out the when key. I don't need a 3rd column. I can adjust and all this business. Okay. And inside this data grid, we have a repeating panel, which is a component that has a property called items, and you can give that anything that any Python iterable object, and so lists or something more complicated like generators, and it will repeat this chunk of UI, which is of course a class, for everything it gets out of that iterator. So what we want to do here is we go to the constructor, and we want to get those database rows from the server and stick them into the repeating panel. So we go to set the repeating panel's items property to be the return value of anvil.server.call get visitors. There we go. And you can see Testy McTesterson has joined the chat. One more thing. So what we're getting here is, just naive readout of what's in the table. This is just what you get when you call stir on a date time. It's not very pleasant. So let's go fix that. Let's fix our date formatting. So we go in and we edit this chunk of UI. Instead of taking the default behavior, we're going to stick a label into this column. And then we're going to say that the text on this label should be bound to this Python expression. Now, self.item is an object that is the row from the visitors table. It's been just passed from the server to the client as a return value from a function call, and now we can use it in the UI. These objects are accessible like dictionaries, so I can just pull out the when column, and of course that's going to be a datetime object, which means I can call stir time on it. Easy peasy. Let's run this thing. There we go. We're formatting the dates nicely. Ah, yes. So somebody has been trying SQL injection here, and this is another example of the cost that having all these overlapping abstractions gives you, because SQL injection comes from the fact that you're generating source code from one programming language in another. Whereas if you keep everything inside an abstraction of, well, these are just Python values, then you close off the opportunity to do things like accidentally giving yourself SQL injection, because a lot of those errors happen at the boundaries between abstractions when people get their mental model of their code's behavior wrong. All right. So I've taken you on a brief whistle-stop tour of this shiny new abstraction. And I'm now going to spend the rest of this talk tearing it down. Because remember, all abstractions fail. And so you don't get a choice about this. Abstractions fail. And therefore, the interesting question is what happens when the abstraction inevitably fails. Sorry. Now, I'm going to walk you through a few examples of how this might happen and how some historical major abstractions have failed. First example, Windows apps. Let's say that it's the late 1990s and you are writing a Windows desktop application, because those are all the rage. And someone comes to you and goes, so we want this thing to be accessible on this web. And you go, oh. Because if your application is written as a Windows desktop application, I'm sorry to say it, but you're going down with the ship. Your choices are either to completely rewrite your application on top of a different abstraction that can do the thing you want, namely be on the web, or to bite the bullet and say, actually, no, sorry, we cannot do the thing we want. And a whole bunch of companies died in the late 90s by, wishful thinking that they could get away with door number 2. So we really don't want this. If you're designing an abstraction, this is really not the outcome you want to inflict on your users. Some abstractions are less rude than that. Let's take Create React App. So if you have tangled with front-end development, you may well have met this creature. Create React App is a project out of Facebook that automates the process of setting up and configuring the Cthulhu-like build system that is involved in building a modern front-end application. You just sort of invoke it, and it will set up a simplified thing that will then drive your webpack config and your transpilation and your minification and your packaging and all of this business, and give you a much simpler way to configure it. And it has support or plugins for a whole bunch of commonly used front-end technologies. But of course, the front-end universe is huge, and it is very likely that sooner or later, your application will end up needing something that Create React App does not have native support for in its simplified abstraction. And the good news here is you're not going down with the ship, because the Create React App authors have thought up an answer to this, and the answer is Create React App -- eject. And what this does is it takes your configuration and then it writes out a Webpack configuration file that describes what it's been doing so far. At which point you can drop down to the lower level underlying system and add whatever funky new front-end technology you wanted to add. And in many senses, this is good news. You are not going down with the ship here. You could do what you wanted. You weren't, you weren't prevented from doing something that the underlying platform supported. The bad news is that to do it, you needed to pull the ejection handle. And now here you are in the middle of the Mojave Desert with nothing but with your parachute and a survival pack, just because you needed one advanced feature. That's kind of rude. And again, not a great experience. How should we do it? Well, what we want to do is what Python does. I talked earlier about an example of Python's abstraction breaking. You just can't write high-performance numerical code in Python. Interpreter can't do it. Which is a bit of a problem, because of course a lot of the things that people want to use Python for require high-performance numerical code. But what Python has is an escape hatch. And in this case, this is the native code support. So what Python allows you to do is pull up a module that you've written in a high-performance compiled language like C or Rust or Fortran. Yes, you'll probably use Fortran code if you use NumPy. And hook it up so that you can call into it from Python and you can call into Python from it. And what this means is that when your abstraction has failed you, you can climb out of your escape hatch, go do what you need to do, go write your high-performance numerical code, and then climb back into the abstraction you were using. And so you have NumPy, which is written in C, but you can drive it from Python with all the usability and rapid development of Python. Needless to say, this is what we want. This is how you stop an abstraction from becoming a straitjacket. And so I'm going to take you on a brief tour of how we have created escape hatches in Anvil, because the web platform is huge and we cannot abstract over all of it. So having high quality escape hatches is the difference between the project being useful and being a dead weight. Let's start with JavaScript. The browser is a gigantic platform. It's the new operating system. And all the things that the browser can do, we don't have Python bindings for yet. We just can't. So what we do is we offer an escape hatch that lets you drop into JavaScript. So let me show you. I'm going to pull together a custom HTML form. So let's say that we want to write some JavaScript. I'm just writing it here for simplicity's sake. Obviously, you can put it in a JS file. I'm going to write a JavaScript function. And I want to be able to drive this from this Python code. Let's put a button on here. We want to be able to call that JavaScript function when we click this button. Well, from our Python code, we can just go call self.call.js and pass it. Okay, so we have Python to JavaScript interoperation, but then let's go one better and say, okay, well, we don't want everybody who's using this piece of JavaScript code I'm writing to have to deal with the fact that they're escaping from our abstractions. So I'm going to bundle this up and say, actually, I'm going to use this as a component. So it's got properties. Let's give this one a better name, Greta. I've just turned this little chunk of UI and code into a component that we can now drag and drop onto our UI, just like any other component. And so we've taken something that was nice Unicode testing. We've taken something that was a complicated, awkward, oh no, I have to deal with JavaScript here, and turned it into something we can use as a Python component. We can even drive from the drag and drop designer. So that's JavaScript. What about text editors? I mean, we have a text editor that's built in here with an autocompleter that I could talk all day about, but that's a separate talk. But some people really would you want to have access to this stuff, not just through a browser front end. You want to actually have access to it as files full of text because this is source code. So what we can do is actually make every Anvil application a Git repository. So we can git clone the application, look inside it.
Can you make the text a little bit bigger? Do you mind?
Oh, sure.
Thank you.
Better? Let's
more.
shrinking this down. Can you read this now?
I think it needs to be a little bit bigger.
Right, okay.
Okay, I think we're good. Thank you.
All right. Okay, so you can see I've cloned this application. I'm going in and I'm seeing this as a set of source files. I'm resolving the Vim versus Emacs war by using Nano and making nobody happy. And not just that, but I can then make edits. Commit. Push. And now if I go back to this application, I've got the updated code in here. And so again, this was an escape hatch. I could pull it out, edit it with whatever tools I liked, and then push it straight back into the platform. I haven't lost the ability to use it with the autocompleter. But I have gained the power of using any tool that can talk to a Git repository. Escape hatch, not a data seed. Let's talk about my own computer. So the cloud is an abstraction. The cloud is an abstraction over computers, over the idea of a computer, which is all very well up until you run into something that really does need to happen on a very specific computer. Maybe I have a database running on a specific computer here, and wrong window. And I need to be able to drive this from my application. Well, what we have created is an escape hatch called the uplink. And the uplink is a library you can pip install anywhere in the world. And then you give it this authentication key, and it will connect wherever your Python interpreter is running to your Anvil application. So if I install the uplink library, start Python, run this code, I am now connected to, so this is running on my computer physically in front of me, but I'm connected to the app I just wrote in the cloud. And I now have access to all of those APIs you saw me using on the server. I've just defined a function running on my computer, and now I'm about to call it from my cloud code here. So instead of calling say hello, I'm going to call say hi, which is the new function that I just defined. Now I run this. Oh yes, of course, hello from Nano. And now when I click this button, I've just called a function running on this local computer from the cloud. And once again, this is not an ejection seat. All the APIs I'm using here are the same as I could use in my cloud-hosted server code, which means that I can move code backwards and forwards between the two. I'm not locking myself into one way of doing things, but I am not forced to rely on the abstraction of the serverless cloud. What about things that have to happen really, really entirely on my own computer? You know, I cannot rely on the existence of the cloud. You know, maybe I'm running some IoT device that really does need to be served off a Raspberry Pi on a particular Wi-Fi network, or maybe I'm writing code that runs at a TV station where if the internet goes down, the app has to keep on running. Well, it's for cases like this that we open sourced the Anvil app server. So there's nothing saying you have to use the cloud one-click deployment option. You can just clone an app with git, pip install Anvil app server, and serve your application locally. And again, it's exactly the same source. It's the same runtime. It's the same source code. You could edit that code, push it back up into the hosted runtime. You're not forced to choose, and you are not forced out of the easy one-click deployment of the cloud service, but you can get there if you need to. So having spent most of this talk talking about how abstractions fail, I want to finish on a slightly more optimistic note by talking about the design principles that we use to create an abstraction people don't want to get out of all that often. What makes for a good programming abstraction? And we have a couple of big principles here. One is that code is good. You're telling a computer what to do, and the best abstraction over telling a computer what to do that humans have invented in the 75 odd years since we started programming these things is writing text in a programming language. There's a whole bunch of hype around no code. It's usually a false promise. Why is it a false promise? Because telling a computer what to do with a drag and drop flowchart is an abstraction that is incredibly leaky. And this is why you often find even no-code deployments that work end up being driven by somebody who can in fact program, because someone who can program can think through the leaky abstraction to what's going on underneath and can successfully drive the system. Get me to the code. Even a UI designer, you saw when I was formatting the dates for that display of the visitors who'd entered their names, I wasn't drawing noodles from something graphical from the database onto the screen. No, I was writing Python expressions. And what that meant was that when I needed to do something like format a date, Anvil didn't have to invent that from scratch. You could just pick up the standard Python tools for formatting a date and deploy them right there in the visual designer. Code is good, get me to the code. Code is the right abstraction for telling a computer what to do. Second and final, be accessible. And if I went out and asked the average programmer on the street what being accessible meant, they'd probably say something like, well, it's got to be simple enough for a novice to pick up. And they'd be right. There's nothing inherent to the complexity of the application I built earlier in the demo. There's nothing about that that's so complex that I shouldn't be able to build it in well under 10 minutes. So yes, this should be simple enough for novices to use and to be able to put together quickly. But that's not enough. Scratch, if you've ever used it, is simple enough for novices to use, but people don't build production systems in it because it is not powerful enough for the professionals to. You need this for two reasons. One is for the novices' benefit, because if you stick them in an abstraction that's all like cotton wool, it's like a playpen, then they don't get an opportunity to grow. They can't grow in power and build more complicated and powerful things. And secondly, it's important for the professionals, because just because I, for example, can write 5 different programming languages doesn't mean I want to, and it doesn't mean that my manager wants to wait for me to do it either. So if you're building an abstraction over the web, we were aiming to be simple enough for novices and powerful enough for seasoned professionals. And I know I say this and I can kind of feel the eye rolls from the other side of the world, because we've kind of been trained to think that this is not possible. And I want to tell you that this is not a pipe dream. And that we should know this is not a pipe dream, because we are literally here at a Python meetup, right? Python, the language, the abstraction that hits both of these square on the head. Python is the first thing that an 8-year-old will encounter on their first Raspberry Jam. And it's what powers Instagram, and it's what DeepMind used to be able to beat the human mind at Go for the first time in recorded history. It is possible for a programming abstraction to be simple enough for novices and powerful enough for seasoned professionals, and it is only the garbage fire of the modern web that ever makes us doubt it. Thank you very much.